Hey, so in this video I'll be going over Dropout and the main idea of how it works, as well as showing a graph of like the way it affects accuracy in a neural network. So it works by temporarily disabling random neurons while training in the mini batch and then adjusting the weights and biases. The input and output layers remain untouched because people have often found out if you do dropout on input and output, it usually negatively impacts the accuracy. Sometimes dropout in the input layer is implemented, but it's kind of rare. So after the mini batch is done and the neurons are enabled, and then you choose like a different random set of neurons to disable after each mini batch. So you only do dropout during trainings because you don't want to negatively impact the accuracy during testing. And since there's going to be more neurons enabled during testing, you need to decrease their output values by the proportion of dropout. So if there's p amount of neurons enabled, like p percentage, let's say half of them are enabled during dropout, then when you do testing with all the neurons, you need to multiply their outputs by p. So like you would need to half their outputs since there's twice as many neurons. So if we look at an example during dropout, the weights and biases will learn to work properly with like with half the neurons here, like I just mentioned, and then you would need to half the outputs when twice as many neurons are here. And so the reason that it's effective in overfitting, like people aren't really sure, but there has been papers written that connect it to the human brain and stuff like that. So as well as the main idea of like, if you had 10 neural networks attempting to classify the handwritten digits and you took the most common output from the 10 networks, you would have a much more accurate result. But this is not really an efficient way of reducing overfitting or getting more reliable predictions. So another way to do it is by using dropout, because in some way you're training like many different neural networks, like many variations of the same network with different nodes. So the nodes learn to not depend on specific weight values or specific nodes. So they kind of become more resilient and more like versatile, if that makes sense. So it's similar to training more neural networks without the additional cost of training more networks. And usually this is much more effective if you're training for long periods of time, like hours on a GPU or something like that, because it takes a lot longer to converge with dropout. So this paper here, I recommend you read. They discuss dropout and how it reduces overfitting, and they pretty much go over the same idea. Like that, if you had unlimited computing power, you would just run a bunch of neural networks at the same time, but that's not really efficient, so dropout fixes the problem. There's many different combinations of thin networks, of networks that have neurons dropped, and they kind of explain this analogy of like reproduction in animals and how it gets more diversity in their neural networks, if that makes sense. And they also give the idea that it's more effective when it's coupled with maximum regularization and large decaying rates, as well as momentum. So you can read about that in their paper. It's quite interesting. So to implement it, it's kind of a simple idea. You just make an array of all your neurons, and then you set the values to 0 to 1, and if the value is above your dropout rate, then set it to 0, else set it to 1, and then you can multiply the outputs by this array. So some of them are going to get muted, and some of them will stay the same if they're multiplied by 1. So this is just an example of 10, 15, 80% dropout. 80% dropout affected it negatively, but this is mostly because this is only 100 epochs, and this is like a super simple neural network that is just used to classify handwritten digits. So it's not the ideal situation for Dropout. But there have been papers that show stuff like this. This is super impressive, and it kind of shows how the baseline is here, whereas using Dropout's like up here. And too much Dropout, like 80%, is obviously negative, and you can see how the more Dropout there is, the longer it takes to converge. So this red line here is at 60% Dropout. It does converge at a high value, but it just takes longer. So it takes more epochs, and it takes a more deep neural network. And you can read their paper here if you're interested. And yeah, that's pretty much it for this video. I'll talk about data augmentation and some other stuff in future videos. And yeah, have a great day.